So the reason we're going to talk about curves, one-dimensional curves, is that we're going to integrate along curves. And when I first saw this, I was a little bit puzzled, because when you learn about integration from calculus, you learn about integrating over intervals on the real line. You're doing calculus on the real line. So I expected integration on the complex plane to be integrating over the entire complex plane or open subsets of the complex plane. And then suddenly the discussion was about integrating over one-dimensional curves. And it seemed not completely natural to me, but there's a reason for this. And the reason is that what we want integration for is to apply the fundamental theorem of calculus. So the fundamental theorem of calculus is a one-dimensional idea. It's a one-dimensional concept. So brief recap. If we have in the real line some function like this, equal to f of a minus f of b minus f of a, like this. And what is it doing? It's an exactly perfect example of the yin and yang in calculus. So calculus, we introduced this more generalized form of addition, which is integration. We have the concept of differentiability that allows us to understand things on a very, very small scale, right? So we're adding up these very, very small changes, the very small differences in this generalized way to find the total net difference. That's the fundamental theorem of calculus. Yeah? And the easiest metaphor is to think about f as being position, f prime is speed. So if we integrate up these speeds, we have the total distance, well, the total net change in position. Yeah? It's a one-dimensional idea. We have these little changes going in one dimension, in this case, along the real line, how much the function is changing as we go from x to x plus h, right? And this thing, this quotient is this number, right? And we're adding together all these tiny, tiny changes to find the total change, total net change. Yeah, it's a one-dimensional idea. There is a higher dimensional version of the fundamental theorem of calculus, and that's the divergence theorem, Stokes' theorem. But the fundamental theorem of calculus, where we assess change, means going along in a one-dimensional line. Okay, and we're going to want to do that in the complex plane, yeah, which means we're going to be integrating on one-dimensional lines, and we want to see how much complex value changes as you go from the start to the end. Yeah, so we start the discussion by trying to understand what we mean by curves in the complex plane. So this part is kind of a recap of what you learned in multivariable calculus, hopefully. Yeah, so we start with describing a parametrized curve. So and this is going to be a function. C goes from A to B into the complex numbers, okay? And it'll be continuous. Oops. Now, we will generally want a smooth curve. So a smooth parametrized curve. So from now on, parametrized gets abbreviated to this, is where z is differentiable on A cubed b, the derivative is continuous, and differentiability is pretty easy to understand, right? So this is just this thing. I'm going to take the limit, so it's mapping from something in the real line to the complex numbers. So we take this limit, as h goes to 0, of z of t plus h minus, oops, z of t over h. This makes sense, right? This is a complex number. This is a complex number divided by h. If this limit exists, then we write z prime of t, and this is itself a complex number. Yeah? Nothing about this uses the field properties of the complex numbers. So I could be doing this from the interval into R2. It would look exactly the same. And then what is the meaning of this thing here? Well, it is just this little vector here, which goes along in this direction, right? So if this guy is point v of t, right? V prime of t is what happens when we move forward a little bit, minus to where we are, divided by the h, right? And we take the limit. Yeah? Cool. So it's clear that this vector, when I say vector, I mean identifying complex numbers as members in R2. It's clear that this thing here is pointing along the direction of the curve if it's smooth, yeah? Tell me about the length of this vector. Yeah, so the length of this vector depends on how fast our parameterization is going across this set of points, right? So this thing here could be the image of z over some interval ab, right? And we can create another curve that will go exactly across the same set of points, right? In which case, when we take the derivative of that curve, it'll still be exactly tangent to this one-dimensional curve in the plane, yeah? However, we could have a completely different speed in which we go along these points, yeah? Yeah? So z prime of t is the speed as we travel along this set of points, right? Yeah. So this is a kind of a hint that the parameterized curve and the actual set of points in the plane that we think of as a curve, that's what we naturally mean by a curve, not exactly the same things, right? We can have different parameterized curves describing exactly the same set of points, yeah? So this is something we're going to have to face shortly. Yeah? But just to the mechanics of it, just the formalities of it, this is what we mean by a derivative. This is a geometrical meaning. And we often want to have that there is some half one-sided derivative at the endpoints, because we're going to deal with closed intervals and we're going to stitch them together to have piecewise smooth curves. So you often want the one-sided derivatives to exist. And like this, a prime of a. So if we're doing a, then we can only, so this thing doesn't require any sign on h, it's just h goes to 0 in any way. But if we are here at the endpoint, then we can only move forward. So then this is the limit as h goes to 0 from the right-hand side from positive numbers like this. Okay. So it's one-sided because we're only going for positive numbers. And z prime of b, maybe I should put a quotation marks because it's not strictly a derivative. I don't know, like this. And I like to write it like this. So let's again take h going to 0 from above, but now I want to write it like this. So this we are b, and we're going to, so it's going to be z of b minus z of b minus h over h. And that thing is the same as, this is also the same as this. It's the same as the limit as h goes to 0 minus of z of b plus h minus z of b. But I prefer to write it like this. Okay, so these are one-sided limits that we want to have. So then there is some kind of a tangent here and here. Okay, so that's what we mean by a smooth parametric curve, except we also have the condition that z prime of t is not equal to 0 No, it's okay, it's a complex number. Z prime of t is not equal to 0. What a mess. For any t inside the open interval AB. Well, actually, since we defined this, we can do it anywhere. Like this. So that's what we call a smooth parametrized curve. Cool. All right. So as I was kind of alluding to, the set of points in the plane which we think of as the curve and the parametrized curve are not the same things, right? So we think of the actual image of this thing as being the curve. Okay, and we want to formalize that in some way, and the natural way is as follows. So if we have some other function, say w from CD into the complex plane, such that the image is the same as this guy, okay, then we'd like to have them be the same in a more precise way. We'd like to say that they are really equivalent, and we will do this in the language math as follows. We say W is equivalent to Z if and only if there exists a bijection let's call it S from A to B into C to D, running out of space, where we can go from one to the other via this bijection. So we have that Z of T is equal to W of S of T, and S prime of T is bigger than 0 for our T between A and B. Okay, that thing is what we use to say that these two curves are equivalent. Okay, so as I raise the board, look at this S of T. Tell me about what the graph of S of T looks like. So this is our condition that, so we have that S goes from A to B into C to D, where S is a bijection, and S prime of T is bigger than 0, and put it over here, I guess, and Z of T equals W of S of T, like this. Okay. So what is this thing doing? This thing is reparametrizing the interval AB, right, to the interval CD. So this condition in particular implies that, let's call this thing star, implies that the images of both those things are exactly the same, right? Z of the interval AB is the same as W of the interval CD. So the set of points that are described by this are identical, yeah? But the S itself is reparametrizing the interval AB, so this would be AB, to the interval CD, okay? And you can think about this as a kind of rescaling of time. So a nice metaphor to think about functions from the interval into the complex numbers or into the plane is to think about it as the motion of a flying bee with respect to time, right? So you can think about as t goes to z of t is the position of the bee at time t. So if we start here at z of a, then we move along, and we end up here at z of b. Yeah? That's how we can think about a function from an interval into the complex numbers. And what this thing is saying is that we start at the same, let me change color. We start at the same place, W of C, and this is W of D, okay? And for every time between A and B, it is stretched or shrunk to some time along here in a bijective way. So for example, from here to here could be stretched from here to here, but then from here to here could be shrunk from here to here, right? Yeah? All that stuff is fine, yeah? So it doesn't have to be in any way a regular rescaling of time, it just has to be bijective. Just has to be bijective, yeah? So if we're going to do a graph of this thing, what would it look like? S to B, so this is A to B, and this is C to D, say. Then it is an increasing function. We know it's increasing just because it's got to be bijective. If it wasn't increasing, then it wouldn't be bijective, and this would change things completely, because we just want to rescale time with respect to this function S. It's better to use a different color. However, to be bijective, we don't need that S prime is strictly bigger than 0 everywhere. But we add this condition just because it makes things nicer. Okay. So this is what S is doing. This is our function S. Okay, good. And yeah, just think about this as a rescaling of time. So imagine putting a tape measure here. So imagine putting a tape measure here with your like 1 inch, 2 inch, 3 inch, whatever. And then the tape measure is just messed around with. So we're going to stretch some parts of the tape measure and we're going to shrink some parts. And then we have like this happening, perhaps. Something like this. We can stretch and shrink it however we want. Yeah? That is all that this function S is doing. It's rescaling things, rescaling time. However, this is useful because now it allows us to divorce the concept of the curve from the actual parameterization. Because what we're actually interested in is this one-dimensional curve in the plane rather than the parameterization. Yeah? So now we can, in the language of math, define what a curve is. So we say a curve. Firstly, we say that, well, I think we've already said, we say that two parametrizations are equivalent if there exists such an S. Let me repeat that. We say that W and Z are equivalent. Okay, and we say, and we define a curve to be the equivalence class of all equivalent parametrizations to some particular choice of parametrization. So our particular choice that we started with, Z, is just one particular, it's like the representative of the equivalence class. Yeah? So that is maybe seems somewhat of a cumbersome definition for this concept of a curve, which seems rather natural to us. However, it is at least a clear one, a one that makes sense to us, and that's what we call a curve. So I'm not going to make a kind of big deal about this from now on. All we can take away is that whenever we have a curve in the plane, we can choose whatever parametrization we want, and that one will be fine for us. Okay, and everything I'm going to do, if it makes sense, will be independent of our parametrization. But to actually calculate things, we're going to need to use a parametrization, but I claim everything which we do going forward won't depend on it. Okay, cool. So another thing to say, finally, is that there is inside this an implicit orientation. Because on the real line, we make the convention that A is less than B. I mean, we're not going to make the convention, but we agree that A is less than B. So this thing here, Z of A, we think of as the start. And Z of B, we think of as the end. Yeah? So every curve has an implicit orientation. Yeah? There is some choice of the start endpoint and some choice of the end endpoint. And for every equivalent parameterization, the start endpoint is the same and the end endpoint is the same. Yeah? Cool. Okay, cool. So that's what we mean by curves. And let's do a little bit more algebra of curves and do some examples of curves. So this leads us to the concept of having a curve with the opposite orientation. So we will denote a curve by this thing, gamma, okay? And we define gamma minus. Informally, gamma minus is the curve which has its endpoints flipped. So the start point of gamma will become the endpoint of gamma minus, and the endpoint of gamma is the start point of gamma minus. Okay? So if this is gamma, we can think of this as having orientation going from the start to the end. Okay? And gamma minus will be a set which covers exactly the same set of points in the plane, in the complex plane, but the start and end point are reversed. And this obviously is important when we do calculus because, as I said, the point of doing this is to allow us to do the fundamental theorem of calculus in the complex plane, and we obviously have to make a choice of start and end. And on the real line, it's trivial. The lesser number is the start, the bigger number is the end. In the complex plane, there's no obvious choice. It's implicit in the curve, right? So when we have a curve, we have to make the choice of what is the start and the end. And sometimes we want to go the opposite way, right? So we'll define it like this. And then formally, how do we get to such a thing? That should be D, E. Like this. How do we get to such a thing? So how do we define such a thing? So given a parametrization of a curve, let's call it Z. Just for generality, I'm going to take Z from A to B, interval A to B, but I can always take Z to be from 0 to 1, right? Because we've now learned that we can reparametrize, and that'll give us exactly the same. Well, let me say that better. We've now learned that a curve is an equivalence class of parametrizations, of that set of points. So we could always reparametrize A, B to 0, 1. And if you want, in your homeworks, whatever, you can always take 0, 1 because for obvious reasons, 0, 1 can be mapped to AB with a mapping S that is differentiable, monotonic, and all the properties that we need. So we say this guy over here, or say this guy is a parametrization. So maybe just to emphasize this, I'm going to write, no, I won't, I just write complex numbers. So that this guy is a parametrization. We define let's call it Z minus, like this. Again, from A to B, like this, as Z of A plus B minus T, okay? So this is a definition, and let's see what Z minus does. So Z minus of B, when you put B inside this, we're just going to get Z of A, and Z minus of A, we put A into this, we're just going to get B, or Z of B. So this guy is exactly reversing the orientation, right? So this guy is starting where our Z ended, and it is ending where our Z started, right? Do you see what I mean? Nod your head if you're with me. Now give me actually a thumbs up because it's hard to see head movement. All right, good. So this guy is a parameterization over the same set of points, but now the orientation is reversed. And gamma minus is the family of equivalent parametrizations to Z minus. I should say equivalence class, but family, same thing. To Z minus like this. Okay, so we have a notion of a curve and then the negative curve, the opposite orientation curve.